My name is Elizabeth Wyss, and I'll be presenting me and my colleagues' work on What the Fork? Finding Hidden Code Clones in NPM. The high-level takeaway of this work is that code bases that are copied and re-uploaded to a package repository lack necessary provenance information that impacts the security and usability of those package repositories, which are crucial to modern software infrastructure. To our knowledge, this work is the first to categorize and analyze this phenomenon within the domain of language-based package repositories, particularly NPM. And to address this phenomenon, we construct Unwrapper, a detection pipeline capable of identifying issues posed by copied codebases and restoring their missing provenance link in real time while scaling with the growth of NPM. Now, I'd like to outline the rest of this talk. First, I'll discuss necessary background information and provide the motivation that inspired us to engage in this work. Then, I'll describe the high-level design of our tool, Unwrapper. Afterwards, I'll discuss how we evaluated Unwrapper and its overall effectiveness. And lastly, I'll conclude the talk with some recommendations and next steps in moving forward from here. Now, let's get into some needed background material. First is the software supply chain, which refers to all of the people and processes involved in the creation of software. And a key consideration in the software supply chain is that if any part of the supply chain is compromised, then the final deployed software is affected by that compromise. And next, I'll discuss NPM, which is the world's largest open source package registry, hosting over 1.9 million JavaScript packages and a key component of many modern software supply chains, like this one pictured on the right. Additionally, there's two important background details of NPM that are very relevant to this work. First is that it's known that some packages contain vulnerabilities, and these vulnerabilities can be identified in installed packages by running an NPM audit. It's crucial for vulnerabilities to be tracked accurately so that NPM's auditing feature can identify known vulnerabilities. And second is that NPM lacks a mechanism for forking packages. Because of this lack of an explicit fork, there exists a phenomenon where a package creator copies an existing codebase, potentially makes some modifications to it, and then re-uploads the package's codebase to that repository. In essence, this creates a stealth fork that lacks provenance information. This stealth forking phenomenon explains one of the key findings of this work, that code clones, or copied code repositories that lack an explicit mechanism linking back to their source repositories, are endemic to the NPM software ecosystem. Within this domain, we term such code clones as shrink-wrapped clones because they're often analogous to the shrink-wrapping feature of such repositories by which packages can be installed and locked into older, previous versions. While we believe that the shrink-wrapped clone phenomenon generalizes to other language-based package repositories, we focus our study on NPM because it's the largest and most popular of such repositories. More specifically, shrink-wrapped clones are comprised of two distinct types of clones. First is identical clones, which contain source code that is identical to that of an existing package. And second is close clones, which make potentially significant syntactic and/or semantic changes to the code of an existing package, but these changes are generally localized to a small number of files. Now, I want to show a motivating example illustrating how shrink-wrapped clones impact the security and usability of the software supply chain that spans the process of software development to deployment. So suppose that a repository hosts an original package, but this package has a code issue. Over time, the issue is discovered and the package is patched. Now, when a developer installs and uses the package, they're directed to use the patched version of the package. And this means that the final application they deploy is also patched. And this is the desired outcome. However, the existence of shrink-wrapped clones complicates this process. Now, suppose that the original package with a code issue is cloned and re-uploaded to the repository. In this scenario, when the code issue is discovered in the original package, the issue disclosure doesn't propagate to the clone package, and the code issue remains unpatched. If a developer installs and uses the clone package, either by choice or confusion, or indirectly as a dependency of another package, then that code issue will exist in their deployed application, leading to a vulnerable application. This problem is further exacerbated because the vulnerability in the final application already has known exploits that were discovered in the original package. To be more precise about the dangers of shrink-wrap clones, we identify two main issues that these clones pose. First is that they increase package confusability. With the existence of clones, it becomes harder for developers to distinguish between packages and to select the correct package that they intend to install. And second is that clones perpetuate poorly maintained, less vetted code. We find that shrink-wrapped clones often lack regular updates and scrutiny as compared to the packages that they clone, and this works to perpetuate the existence of code issues in these clones. We find that the issues posed by shrink-wrap clones can be addressed by identifying the missing link between clones and their source packages, restoring needed provenance information. When this link is restored, it enables three important features. First is issue discovery propagation, so that issues discovered in the source package can also be identified and disclosed in the clone package. Second is improved code transparency, so that it's easier to see where a piece of code came from and how it evolved over time. And third is more informed package selection, so that when a developer seeks to install a package, they know which packages are clones and they can more easily identify the package they intend to install. Now that I've discussed the background and motivation of this work, I want to get into the high-level design of our tool, Unwrapper. Once we knew that we wanted to build a tool that can identify shrink-wrapped clone relationships, we encountered three main challenges that the tool had to overcome. First is the challenge of ambiguity, which captures that it's difficult to discriminate the extent of code reuse that constitutes a clone. This is a well-known problem in the field of code clone detection, and it's one we had to consider in this work as well. Second is the challenge of complexity, which expresses that close clones can exhibit quite complicated syntactic modifications, things like converting an entire package from one ECMAScript module format to another. And third is the challenge of scalability, which captures that packages must be checked against the entirety of NPM to identify clones, leaving little to no time for analysis and imposing a very tight performance constraint on the system. The main component of our tool Unwrapper is its clone detector. The clone detector takes a clone candidate pair as input and outputs whether the two packages have a clone relationship. The key insight behind the clone detector is that package clones will largely share in identical files. Here's how the clone detector operates. For an input clone candidate pair, the clone detector first computes the file-level checksums for each package. We chose to operate at the file level because it overcomes the complex syntactic modifications imposed by the challenge of complexity. These checksums are then used to calculate a difference score heuristic that captures differing files in each package. And lastly, clone classification is performed via a tunable threshold over the clone candidate pair's difference score. Using a tunable threshold overcomes the difficulties in precisely defining a clone imposed by the challenge of ambiguity. Now, I want to describe the clone detector's heuristic in a little bit more detail. The pairwise difference score between two packages is defined as the number of identically named files with differing contents, plus 2 times the number of files unique to either package. And then package pairs within a given difference score threshold are classified as clones. This heuristic captures pairwise file tree similarity at a high level with low computational effort. Although the clone detector overcomes challenges related to clone detection, we found that it's not a very scalable approach. To address this, we built a high-performance pre-filter designed to approximate the output of the clone detector by quickly weeding out packages not likely to be clones. The pre-filter takes a single package as input and outputs a list of packages that the input package has a possible clone relationship with. The key insight behind the pre-filter is that packages with dissimilar file trees are not likely to be clones of one another. Here's how the pre-filter operates. First, the pre-filter calculates a fingerprint of the input package, which is the set of hashes of the file paths within the package's file tree. Then, the pre-filter compares the fingerprint of the input package to an in-memory fingerprint dataset of all of NPM. This cached fingerprint dataset allows the pre-filter to very quickly compare a package against all of NPM, thus overcoming the challenge of scalability. And lastly, potential clone candidates are identified using tunable thresholds over file tree overlap and file tree size difference. Now, I'll describe the pre-filter's heuristics in a little bit more detail. The first heuristic captures that clones must have file tree size differences within a given threshold. And this is because packages with vastly different file tree sizes are not likely to be clones of each other. The second heuristic captures that clones must have file tree overlap greater than a given threshold. And this is because packages with little overlap in their file trees are not likely to be clones. These heuristics require very little computational effort with cached fingerprints, as is how the prefilter is constructed. These individual components come together to form Unwrapper, a tunable, heuristic-based shrink-wrapped clone detection pipeline that overcomes the challenges of clone detection. Unwrapper is composed of three main components. First is an NPM interface that automatically fetches newly uploaded packages for clone analysis and feeds them into the clone prefilter. Second, the prefilter tests an input package against all of NPM to quickly weed out packages not likely to be clones. And lastly, clone candidate pairs output by the prefilter are fed into the third component, the clone detector, which analyzes them in greater depth to accurately classify clones. Now that I've discussed the design of our tool Unwrapper, I want to get into how we evaluated it and how it performed in that evaluation. We evaluate Unwrapper's performance to verify that the system overcomes the challenge of scalability. The clone prefilter can add a new package to the clone prefilter's fingerprint dataset in just about 5 milliseconds, and the prefilter can test a package against all roughly 20 million unique versions of NPM packages in just about 70 seconds. And the clone detector can test a single clone candidate pair in about 255 milliseconds. We compare these metrics to NPM, where a new package is uploaded every 101.6 seconds. Therefore, Unwrapper does indeed scale with the growth of NPM in real time and passes the challenge of scalability. We evaluate Unwrapper's effectiveness in detecting clones to verify that the system overcomes the challenges of ambiguity and complexity. The prefilter was evaluated using the output of the clone detector because the prefilter was designed to approximate the output of the clone detector. On a dataset of 6,292 clones identified by the clone detector, the prefilter achieves an average recall of 95.3% with a median of 8 false positives reported, meaning that it's typical for the clone prefilter to forward no more than 8 false clone candidates to the clone detector with a given input package. And the clone detector was evaluated by sampling 100 clones identified by the clone detector and manually verifying the identified clone relationships. Within this sample of 100 clones, we find that the clone detector achieves an average precision of 94%. Overall, we believe that these metrics illustrate that Unwrapper is practical and effective at identifying clones, thus passing the challenges of ambiguity and complexity. The big finding of our work on Unwrapper is that clone packages are frequently more vulnerable than the most up-to-date version of the packages that they clone. And in a non-negligible number of cases, existing tooling can't detect these vulnerabilities. We find that 63% of identified clones are as vulnerable as the original package. Another 34% of identified clones are more vulnerable than the original package, but these vulnerabilities can be detected by NPM's auditing feature. And in 3% of identified clones, they're more vulnerable than the original package, and these vulnerabilities cannot be detected by NPM's auditing feature because the vulnerabilities were copied over from the original package's codebase directly. Another key finding of this work is that clones are often poorly maintained. They tend to be very rarely updated. This matters because regular package maintenance is needed so that bugs and vulnerabilities are addressed in a timely manner. We find that 47% of identified clones have 0 package updates. Another 20% of identified clones have only received a single package update. Another 23% of identified clones have between 1 and 5 package updates, and only 10% of identified clones have greater than 5 package updates. We believe that this lack of maintenance poses significant problems for the health of the NPM ecosystem. Now, I want to share some other interesting details related to package confusability introduced by clone packages. The first detail deals with the total clone relationships across NPM. From analyzing a random sample of 6,000 NPM packages and extrapolating the results, we estimate that up to 10% of NPM packages may belong to one or more clone relationships. This number may seem high at first, but it's important to note that it includes all packages belonging to either side of clone relationships. In other words, both clone packages and packages being cloned. Additionally, clone relationships are often one-to-many, as in a single popular package may have many clones, which further raises this number. The second detail deals with name similarity between clones and their source packages. We utilize a fuzzy name similarity heuristic based on whether one package's name is a substring of the other. And from analyzing the 626 clones identified in the random sample of 6,000 NPM packages, we find that 28% of identified clones have similar names to their source packages. These details further exacerbate issues of confusability posed by shrink-wrap clones. We also have additional details and analysis of clones in our paper that you can check out if you're interested. Now that I've discussed the evaluation of our tool Unwrapper, I want to get into some next steps and where we go from here. As shown in our analysis, code clones pose ecosystem health concerns for language-based package repositories like NPM. They increase the confusability of packages, they decrease the transparency of code in the repository, and they perpetuate known vulnerabilities while evading auditing. If there existed an explicit forking mechanism, restoring the missing link between clones and their source packages, these issues posed by clones could be mitigated. While our tool Unwrapper is effective in restoring the provenance information needed by clones, this functionality should be officially supported in NPM. We believe that NPM and other language-based package repositories should implement an explicit forking mechanism. We also believe that Unwrapper could aid in retrofitting existing clones as official forks and enforcing that future clones are converted to forks. To conclude, the security and usability of the software supply chain is impacted by the shrink-wrapped clone phenomenon analyzed in this work. To address this, we built Unwrapper, a shrink-wrapped clone detection pipeline capable of restoring the missing link between clones and their source repositories in real time. We believe that Unwrapper is an important step towards mitigating the threat of shrink-wrapped clones and improving the hygiene of language-based package repositories. Thank you.